Hi, this is the second part of the solving trig equations. We'll get to see some other formulas and work with a couple of additional ways to solve these problems. So the first one says, solve on the interval from 0 to 2 pi, answer with exact values where possible. So here's something that involves tangents, right? Tan squared, a tan, and a 1. First thing I do is see if this is factorable. And it looks like it might be. I'll put a 3 tan x over here and a tan x over there, because I know when I multiply them, I'll get tan squared. The only factors of 1 are 1 and 1. Both signs are positive, so let's put pluses here. FOIL it back out, I'll get a 3 tan squared. 3 tan plus 1 tan gives me 4 tan. 1 times 1 is 1. All right, so far so good. So either the first term is 0, 3 tan x plus 1 is 0, or tan x plus 1 equals 0. If I solve this over here, I get 3 tan x equals negative 1, or tan x equals negative 1/3. Over here, I get tan x equals negative 1. Well, tan x equals negative 1, I can answer with exact values. The tangent is negative 1 in the second quadrant at 3 pi over 4, and in the fourth quadrant at 7 pi over 4. So those two I've got. The tangent is equal to negative 1/3 at two places that I don't know because they're not nice numbers on the unit circle. So I will take my calculator and throw in the inverse tan of negative 1/3, and my calculator returns x equals negative 0.322. But you notice negative 0.322 is not on the interval from 0 to 2 pi. So what is someone to do? Well, remember these tangent things repeat every pi. So if I have a negative 0.322, let's add pi to it. When I do that, I get 2.82. Okay. But there's another solution. Remember we said the tangents repeat every pi. So just like 3 pi over 4 plus pi gave me 7 pi over 4, take that 2.82 and add pi, and the other solution is 5.96. So there's four answers. 3 pi over 4, 7 pi over 4 are my exact values, and then 2.82, 5.96 are my approximations, understanding that because of the restricted values for inverse tangent, my calculator didn't give me an answer on that interval, so I had to take the negative 0.322, add pi to get 2.82, add pi again to get 5.96 because the tangent has a period of pi. All right, let's take a look at this one. Again, this question says solve on the interval from 0 to 2 pi. I could take cosines and turn them into sines, sines into cosines. It's easier to turn cosine squares into sine squares because my middle term has a sine of x. So it would be best if I could have a sine squared of x. So remember how the formula goes. If sine squared plus cosine squared equals 1, then cosine squared is 1 minus sine squared. So I get negative 4 times 1 minus sine squared x minus 8 sine x plus 7 is equal to 0. Let's clean this up a little bit. Negative 4 times 1 is negative 4. Negative 4 times negative sine squared is positive 4 sine squared minus 8 sine x plus 7. So I've got a 4 sine squared x, a minus 8 sine x, and then a 7 plus a negative 4 gives me a 3. Now, maybe the hard part for you is factoring this. If you don't like dealing with it like that, you could always come on the side and do one of these little substitution deals where you say, instead of sine, I'll use like a p. So I can use 4p squared minus 8p plus 3. And you could even do a AC method factor by grouping type thing where you say, I'm looking for two numbers that multiply to be 12 and add up to be negative 8. So factors of 12 that add up to negative 8, I'm going to go with negative 6 and negative 2. So I'm going to replace that negative 8p with the negative 6p minus 2p. and then I group. So I'll group the first two together, put a plus sign, and group the second two together. So pull a 2 out of the first group and pull a p out of the first group, and you're left with a 2p minus 3. Notice that the second term is a negative 2p plus 3 is the exact opposite of what we want. So let's pull out a negative 1. So we make it a positive 2p minus 3. And so when we factor, we pull out the 2p minus 3, and we're left with a 2p minus 1. Well, now go back and replace those p's with sine of x's, and we factored what we were trying to factor. So this one was a little bit messy on the factoring end of it. So the 2p minus 3 becomes a 2 sine x minus 3, and the other one becomes a 2 sine x minus 1. Double check and make sure it foils back, right? 2 sine times 2 sine is 4 sine squared. Minus 2 sine minus 6 sine gives me a minus 8 sine. Negative 3 times negative 1, positive 3. So on this side, if 2 sine x minus 3 is 0, then 2 sine x is 3, or sine of x is 3 halves. That's going to be a problem, because remember, sine can't be bigger than 1. So the sine of x can't be 3 halves. This part yields no solution. Let's look at the other side. What about 2 sine x minus 1 equals 0? That means that 2 sine x equals 1, or sine of x equals 1 half. If the sine of x equals 1 half, there's two places where that happens. One of them is at pi over 6. The other one is at 5 pi over 6. So sometimes when you're solving these, you will run into factors that give you extraneous solutions, and that's one of them. So there's no place where the sine of x is equal to 3 halves, but there are two places where the sine of x equals 1 half, and those are my two answers. And the work that I did on the side might be a little helpful if you haven't seen factoring for those harder problems before. You can, by the way, just do a basic guess and check, which is how I did factoring for many years. Just try different multiples of 4 and 3 until you get to a factoring that works. All right, how about this one? Sine squared x equals 4 minus 2 cosine squared x. Well, here we've got both sine squares and cosine squares, so we can actually switch them back between either one. Here, let's turn this cosine squared into a 1 minus sine squared. And so I get sine squared x equals 4 minus 2 times 1 minus sine squared x. And so multiply through on the right-hand side. I get a minus 2 and a plus 2 sine squared x. This gives me sine squared x. 4 minus 2 is 2, plus 2 sine squared x. So we'll subtract the 2 sine squared x from both sides. And this leaves me with a negative sine squared x, right? Because 1 minus 2 is negative 1. And on this side, a 2. Well, we could multiply both sides by negative 1, and we come up with a problem. We come up with sine squared x equals negative 2. So there's no place that the sine squared will ever be a negative 2. There's no place that sine will ever be negative 2. But there's certainly no way that you can square something and get negative 2 out using the set of real numbers. So because that's not possible, there's no solution. Well, what does it mean when I come up with an equation like this that has no solution? Well, let's graph it and find out what happens. All right, so I came over to Desmos and I popped the two graphs in there, right? I put the left-hand side, y equals sine squared x. The right-hand side, I got 4 minus 2 cosine squared x. And look what happens. Here's two graphs that end up in phase, right? Where one hits the max, the other hits the max, one hits the min, the other hits the min. So they're always going up and down, up and down. They never touch each other, right? They never get close enough to intersect. And so that's why it is that when I come up with the algebraic solution, I come up with something that has no real solutions, because when I go to graph it, the two graphs never intersect. Remember, we hit solutions where the graphs intersect. Where do they intersect? In this case, they do not. And so that's why there's no solution. All right. Let's try a couple more, and then we'll wrap this up. So both these say solve on the interval from 0 to 2 pi. First one is cotan plus cosecant squared equals 1. Well, if I'm going to do this, it would help me to turn the cosecant squared into a cotan squared because I already have a cotan. Let's see if I can add a cosecant to that. So let's take the cosecant squared. Right? We should be getting better with trig identities now. We can replace that cosecant squared with a 1 plus cotan squared. And now I've simply got cotan squared x plus cotan x plus 1 equals 1, right? So I rearrange them in order. I put the cotan squared first. I put the 1 at the end. I put that cotan in the middle. Interesting situation, because I got a 1 on both sides. So let's subtract the 1 from both sides, and I get cotan squared x plus cotan of x equals 0. Common factor, let's factor out a cotan x. Take a cotan out of a cotan squared, and I get a cotan. The second term, cotan divided by cotan, is 1. Set each piece equal to 0. So I get cotan of x equals 0. The second possibility is I have cotan x plus 1 equals 0, which means cotan of x equals negative 1. So cotan equals 0 where the tangent function is undefined. Because if I take the reciprocal of 0, essentially I get 1 over 0. So that's where the tangent of x is undefined. Where does that happen? On the interval from 0 to 2 pi, that happens at x equals pi over 2 and at 3 pi over 2. In the second case, cotan is negative 1, where tan is also negative 1, right? Flip over cotan, I get tan, but the reciprocal of negative 1 is still negative 1. So the tangent is negative 1 where I have two values with different signs. Where does that happen? Second quadrant, 3 pi over 4. Fourth quadrant, 7 pi over 4. Signs are different. Numbers are the same without regard to sign. So I got 4 answers. Pi over 2, 3 pi over 2, and then also 3 pi over 4, 7 pi over 4. All right, here we are. Last example of this section. Actually, last example of chapter 5. The excitement is building. Are we ready? So, again, I got a cotan. I got a cosecant squared. I'll bet you I can turn that cosecant squared into a cotan the same way that I did before. 1 plus cotan squared x equals cosecant squared x. In this case, I've also got a 1 on both sides of the equation. So I've got a square root of 3 cotan x plus 1 equals cotan squared x plus 1. Well, if I get rid of a 1 from both sides, I've now got a root 3 cotan equals cotan squared. Bring the root 3 cotan over to the other side. So subtract it from both sides, right? We're undoing operations. And this gives me 0 equals cotan squared x minus square root of 3 times cotan x. Same idea as before, let's factor out a cotan. So if I factor out a cotan of x, I get cotan x minus square root of 3. Because when I pull a cotan out of the square root of 3 cotan x, I just get that square root of 3. All right, so either the cotan of x equals 0 or cotan x minus root 3 equals 0. If that's the case, then the cotan of x equals the square root of 3. So where do these things happen? Well, cotan of x equals 0 here. I'm going to steal from the red problem next to it. That happens at pi over 2 and 3 pi over 2. Same reasons as about 2 minutes ago. Right? Half the problem done. What about the other one? Cotan equals the square root of 3. Well, cotan equals the square root of 3, where tangent equals 1 over the square root of 3. So I'm looking at points on my unit circle where this value over here is 1, and this value is the square root of 3. Remember, they're all divided by 2. So where does that happen? Where is square root of 3 over 2 the first coordinate and 1/2 the second coordinate? That happens at x equals pi over 6. But remember, there must be another point then where both of those are negative, because if I divide sine over cosine like that, I get a positive. So that must happen in the third quadrant, must happen at 7 pi over 6. The other thing I could do is I could just take that pi over 6 that I got in the first one and add pi. So pi over 6 plus 6 pi over 6 gives me 7 pi over 6. And there it is. So that's a little walk through solving some trig equations, some with exact values, some with approximate values.